Hi there. Well, in this video we're going to look at some more examples involving evaluating limits analytically, and I've chosen 4 examples that utilize the following techniques here. And you can 2 of them we've already done. 2 of them in previous videos we've looked at the dividing out technique. In other words, finding common factors in the numerator and the denominator and reducing them, the rationalization technique, which we've looked at, and then the one I've added here is I call it simplifying a complex fraction. So let's just go ahead and get started. And this first function, this first limit I should say, if you look carefully you might be tempted to use the first technique up here, dividing out technique. And it turns out you can do that. You can factor the numerator. You'll get an x minus 2 as a factor. That factor will reduce with the x minus 2 down below, and then you can use direct substitution. Or you can recognize that if we take 1 and plug it in without doing anything, just plug it in, you'll notice that we don't get an indeterminate form here. We do not get 0 over 0. So let's just go ahead and solve this or evaluate it by just plugging in 1. And I get 1 squared minus 5 times 1 plus 6 in my numerator, and in the denominator I get 1 minus 2. Okay, a little arithmetic here. 1 squared is 1, minus 5 is negative 4, plus 6 is 2, over, looks like we have negative 1 in the denominator. And then this clearly simplifies to negative 2. So that's your first example, and I want to drive home the point that before you jump to any of these other techniques, even though as tempting as that might be, just go ahead and see if this guy can get plugged in to your x's and see if you get a number. And if you do, then you're done. Okay, on to the next example. And here it is. If you look at this example, you'll notice that if we plug 5 in, that we get 0 over 0. And that's our indeterminate form. So what we need to do is we need to take our function and we need to change its close. In other words, we need to come up with another function that is pretty much the same thing as this guy. It just might look a little different. And the way we're going to do that in this case is we're going to factor our denominator. Okay, so my numerator is just x minus 5. My denominator is x plus 5 times x minus 5. Okay, so you can see that we really have some common factors here, and these reduce. And when they reduce, we get the following result. We get a 1 up top, and down below I'm left with just an x plus 5. Okay, so now let's rewrite our limit statement and see what we have. We have the limit. We have the limit as x goes to 5 of 1 over x plus 5. Okay, now we can go ahead and use direct substitution. Plugging 5 in for x right here, we get the value of 1/10. Okay, on to the next example. Okay, before I get started on this one, I just want to, as usual, check to make sure that I just can't substitute 4 into my function to see if I can't evaluate this limit just by direct substitution. So if you look, 4 plus 5 is 9. Square root of 9 is 3. 3 minus 3 is 0. And if we plug 4 in the denominator, we get 0. So clearly we cannot just directly substitute 4 into our function here. So we're going to use the rationalization technique in order to turn this function into something that we can use direct substitution on. And what the rationalization technique is we're going to multiply by the conjugate of the numerator. Now if this square root were in the denominator, then I would multiply by the conjugate of the denominator. It just happens to be in the numerator in this case. And the conjugate of this numerator is the square root of 5, I'm sorry, the square root of x plus 5 plus 3. Notice it's the exact same binomial with the exception of this operation right here. This is minus and this is plus. Now, to make sure that we maintain our equality, we need to make sure that we multiply the denominator by the same thing as well. Okay, so notice that this is really just a disguised form of 1. Okay, we're multiplying our original function by 1. Anytime you multiply by 1, you're not really doing anything to it. You might be changing the way it looks a little bit, but you're not changing the value of it. Okay, now the reason we chose the conjugate here is you might think back to Algebra 1 where maybe you had x plus y and you were multiplying it times x minus y. Okay? In other words, you're multiplying two binomials that look exactly the same with the exception of this operation. So when you distribute all of these, you get x squared. This will be a minus, I'm sorry, that will be a, yeah, that'll be a minus y squared. This will give you a positive xy, and this will give you a negative xy. Okay, so you'll notice that these guys are going to drop out and I'm left just with x squared minus y squared. In other words, your middle term drops out. The same thing is going to happen here. In other words, I just have to worry about multiplying this first term, which just gives us x plus 5. Okay, the square root of x plus 5 times the square root of x plus 5 is just x plus 5. And really our last term. My last term here is going to be negative 9. I'm not even going to worry about multiplying my middle terms together because I know it takes on this form right here. Okay, this is all going to be divided by x minus 4 times this binomial right here. And this binomial is the square root of x plus 5. Whoops. Let me erase that little parenthesis there. Sorry about that. Square root of x plus 5 plus 3. There we go. Okay, now simplifying the numerator, we get x minus 4. And I'm not going to multiply these two together. I hope you can see why. We get an x minus 4 in the denominator, and that's going to help us to reduce this function to a point that we can use direct substitution. Okay, so you'll notice that we have an x minus 4 up top, an x minus 4 down below, and if we reduce those factors out, we are left with just a 1 up top divided by this thing right here. Okay, so let's rewrite our limit statement now. And we get the limit as x goes to 4 of, well, we already said we have a 1 up top here. And in the denominator we're left with just this, which is the square root of x plus 5 plus 3. Okay, so now it looks like we can take our 4 and plug it in for wherever we see an x. Okay, so this is going to equal 1 over the square root of 4 plus 5. There's my substitution right there. Plus 3. And if we crunch the numbers here, we get a 1 up top. This is just the square root of 9, which is really just 3, and 3 plus 3 is 6. Okay, so 1/6 is the limit of this function as x goes to 4. Alright, the last example here is one that involves a complex fraction. And we deal with complex fraction. The way to deal with a complex fraction is to try to eliminate it. Okay, fractions are complicated enough as it is for some people. Fractions inside of fractions just make for messy a messy problem. So let's see if we can't try to eliminate this complex fraction. Again, if we check to see if we can plug in 0, you'll notice you get 0 in the numerator, 0 in the denominator. Okay, well, the way we deal with a complex fraction is I like to try to multiply by the LCM of what I call the complex denominators. We really, if you think about this, we really have three denominators up here. We have this denominator that happens to be in a numerator. We have this other denominator, and then we have this kind of bigger denominator. I say bigger because it's kind of like the main denominator of our problem. We want to find the LCM of these. Again, I don't know if this is correct language. I just call them the complex denominators. If I find the LCM of those two guys and multiply the numerator and the denominator by the LCM, some nice things will happen. Well, the LCM of 2 plus x and 2 is simply 2 plus x times 2. And I need to make sure that I do the same to the bottom in order to maintain my equality. Okay, some people get confused right here. Some people, they like to, whenever they're multiplying by fractions, sometimes they have to put that 1 underneath to really recognize that we're multiplying the 2 plus x times 2 times this 1. Well, when I multiply this by this first term here, you'll notice that my 2 plus x up here will reduce with this 2 plus x down below. So I'm really just multiplying 2 times 1, and I get 2. When I multiply it by this second guy, okay, you'll notice that this 2 reduces with this 2, and I'm left with just this 2 plus x. Okay, is really over a 1. Again, this is really an unnecessary thing, but if it helps you visualize multiplying these fractions together up here, go ahead and do that if that helps. Okay, down below, sticking to my technique of not distributing down below, I'm left with x times 2 plus x times 2. And now all that's left to do is to simplify this. 2 minus 2 is 0, and then we have a minus x, which just gives us negative x. Down below I have an x times 2 plus x times 2. Okay, so one thing you'll notice is that we have an x in my numerator, an x in my denominator, and those reduce, leaving us with the following limit statement. The limit as x goes to 0, well, what do we have in the numerator now? Do we have 0 or do we have something else? Well, this is not 0 up here. We're really left with a negative 1. And down below, I'm left with 2 plus x times 2. Okay, this looks simple enough in the sense that we can just go ahead and substitute our 0 in for x. And if we do that, we get the following. We get negative 1 up top, and then down below I get 2 plus 0 times 2. This is my substitution right here. A little bit of arithmetic tells us that this simplifies to negative 1/4. Okay, so negative 1/4 is the limit of this complex fraction as x goes to 0. I hope that made sense. Okay, so just reviewing in summary here real quickly, you'll notice that really the three techniques exercised here. In this example, we used our dividing out technique. In this example right here, we used our rationalization technique. And in this last example, we had to eliminate the complex fraction by multiplying by the LCM of our two complex denominators here. Hope that made sense. In future videos, we will look at some other techniques that maybe involve some trigonometric functions, and we'll save that for a later time. We'll see you later.